I would like to thank the organizers for inviting me to give this mini course. So I will talk about analytic point of view on the delta invariant that was just defined by Hamid at the end of his lecture. And so that will be today. And then tomorrow, I'll talk about generalization of this in weighted kilogeometry, and I will, of course, introduce all this. So it will be really about the number one motivation that Hamid gave earlier for K-stability, which is to find canonical Kähler metrics. But actually, there will be very little K-stability involved, apart from the relation with the delta invariant. Okay, so let me start by giving more precise definitions of canonical Kähler metrics, including the Kähler-Einstein metrics we have seen earlier. So the setting will be, here I'll work with manifold, so meaning smooth varieties. Which are compact complex, in fact, will be Kähler all the time. So you can think of regular projective varieties, that's fine for me, over C. And I'll say that n is the dimension of x, as in Hamid's talk, and I'll take I consider Kähler forms on x. So I remind you what a Kähler form is. So it is a 1-1 form which writes locally as IDD bar of a function. Maybe I should write it where there's no chalk remaining. So this is a way to produce 1-1 forms via complex derivatives. It's not so important. This is on the Kähler manifold, this is true of any 1-1 form. It writes locally like this for some function phi. And this is locally in the Euclidean geometry, smooth topology, but often it works well as well in the Zariski topology. You can sometimes take an affine chart and write this as well. And the edit condition to be Kähler is that this, the matrix that appears here is positive, Hermitian positive definite. And it encodes as well a Kähler metric, which is a Riemannian matrix. Which we may see as this, but that will not matter in the following. That's just to say that I will say Kähler metric for omega instead of G. but it's really about Riemannian metrics in a sense, special Riemannian metrics. So a Kähler metric is this thing, and now we want canonical, so that will be in terms of curvature of the associated Riemannian metric. So we have notions of curvature involved. So first is the Ricci curvature. So this will be a 1-1 form. So as I said, it will also be defined locally as in similar way, IDD bar of a function. And I can use the previous function there to define the Ricci form. Okay, so it may not be very instructive, written like this, but maybe we'll see later that fundamentally this is related to the volume form defined by omega. So up to a constant. I don't need this. So this is really, you build another 1-1 form from the volume form associated to omega, and this is the way you do this. And this encodes Kähler-Einstein metrics. So that's the Kähler form, such that the Ricci curvature of omega is a multiple of omega itself. So that's the first motivation for K-stability, is showing the existence of solutions to this equation from algebraic geometry. Now I want to consider as well more general canonical metrics. So I will not say really much about these today, but I will introduce a general setup that works for these. And tomorrow I shall say some existence results for these more general canonical Kähler metrics. So what you can consider instead of the Ricci curvature is the scalar curvature. Which is a function. So this is a 1-1 form. And this is a function on x. And defined that way, the quotient of these n forms. And this gives rise to a notion, to another notion of canonical Kähler metric, which are CSCK metrics. Yeah, exactly. So these are the definitions of these canonical Kähler metrics, and then there's a fundamental observation, which is the first relation with algebraic geometry. This is that if you study a bit this definition of the Ricci of omega, or maybe take another more standard definition, you will observe that the cohomology class of Ricci of omega is always the first rank class of X. That is the cohomology class defined by the anticanonical line bundle. And this has interesting consequences for both KE and CSCK metrics. So for KE metrics, it implies that either C1 of X is the zero class if lambda equal to 0, or we know what the cohomology class of omega is if lambda is not 0. So we have a strong consequence on the Kähler class if there exists a Kähler-Einstein metric. It cannot be. It can only be on in one of these classes if lambda is non-zero, and then that means either the manifold is Fano if lambda is positive, because there is a Kähler form inside this Kähler class, or it is canonically polarized, the opposite. And then for CSCK metrics, it also gives has a consequence. If omega is CSCK, so a weaker one, but still. So it tells you that, remember this, look at the level of classes. If I consider, if I denote this by S bar, then S bar is the mean value of the curvature. That's of course true if it is constant function. But then these quantities, if S omega is constant, they can be computed at the level of Kähler classes. That becomes C1x as the class of omega to the n minus 1 divided to the class of omega to the n. It's determined, this constant is determined by the Kähler class. And the reason why it's a fundamental observation will come right now, because I will use this to set up the variational approach to the existence of canonical Kähler metrics. So now a crash course on the variational approach to canonical Kähler metrics. So what the fundamental observation says is that it's better to work in a fixed Kähler class. If you want to solve this equation, you fix the Kähler class, then this lambda or this S bar is fixed. You can work on this. So we're going to do this. And we want to characterize, the variational approach says we want to characterize say CSCK metrics as minimizers of a functional. And hopefully that will help in understanding the problem and maybe showing the existence. So now the functional, we want to define it. First, we want to know where it is defined. So that's where we fix the Kähler class. So fix omega, a reference scalar form. Omega 0, it's scalar class, bracket. Then the DD bar lemma on Kähler manifolds, which is here the case, tells me that any closed real 1-1 form in omega writes omega 0 writes as omega 0 plus IDD bar of some function. Smooth function defined on X with real values. So I'll use this to define the space of Kähler metrics in omega 0. I use these phi as a way to parameterize this. So this I will denote by omega phi. And I consider this space. This is K of omega 0. This is the space. It's an abuse of terminology, but call this the space of Kähler metrics in omega 0. If I don't want to abuse terminology, let's say the space of Kähler potentials for omega 0. And any Kähler metric in class of omega 0 writes like this. Okay, so that's the space where I want my functional to live. And then what does it look like locally? Then remark that if I take a phi in K, if I take another function phi dot, which is just any smooth function on X, then for any epsilon small enough, phi plus epsilon times phi dot is in K. The way I'm saying that this is an open subset of this space of functions, but I don't really want to talk about topology now. So you have this property, so you can think of this as a tangent vector. You can think of space of smooth functions as the tangent space to this space of Kähler potentials. Now I can define my functional. It will be the Mabuchi functional.
Does this mean that phi dot can be written as I del dot r or something else?
What it means is I can take any function, smooth function, it will be the tangent vector. I can consider Kähler potentials moving in this direction. This is defined. And then the definition, which is, I mean, there's a statement here, but let's first write it as a definition. There exists a unique functional meaning function, but like a function taking functions, which I write M, which is defined on K with values in R, such that takes the zero value at 0, but that's not important. But more importantly, we impose the way it varies along these tangent vectors. So the variation, the infinitesimal variation of M at phi along the tangent vector phi dot is given by this integral. So I integrate phi dot times the difference between the average scalar curvature and the scalar curvature of my metric omega phi with respect to the volume form omega phi to the n.
Omega phi was not a metric.
Sorry?
You said that omega phi was only a Kähler potential.
No, I mean, phi is a Kähler potential and omega phi is a Kähler metric. Yeah. It's just that.
Oh, sorry.
Yeah.
It's okay. Thank you.
So the nuance is just that there are several Kähler potentials corresponding to the same Kähler metric. Okay, and now did not erase this. This is very much related to this equation. So I'm considering the difference of the right-hand side and the left-hand side. Okay, so to nowhere, no, for now.
Who is this bar? Is it just that definition?
Where is my, oh, over here. If there is a CSCK, then S bar is equal to that, but actually I can define S bar for any Kähler class. Okay, so this is called the Mabuchi functional. Mabuchi K energy, but I'll drop the K energy functional. And
Do you know where comes from this K?
no, that's, yeah, maybe Kähler, but yeah. We don't know, no one knows, I guess. And so this is the functional that we use for a variational approach, and the key properties, so here these are fundamental results that I am putting in a list. These are all theorem. So first, first this is well defined. This is due to Mabuchi. Second, there is a nice geometry on K. Nice being maybe not so nice, but at least we can work with this. So the geometry was introduced by Mabuchi, but nice geometry means that between any 2 points, we can find geodesic joining them. This is due to Chen. And then the functional M is convex along these weak geodesics. So the picture is, I mean, so M is defined on K, takes value is in R, and it's convex. So if K was one-dimensional, it would look something like this, maybe, or maybe something like this, or maybe something like this. And these cases correspond to, I mean, very roughly, that's not really true, but this means, I mean, this picture means M is coercive, and I will define this later. M is bounded below. M is not bounded below. Sorry? Oh, yeah, it should. Well, it's another slice. Yeah, you're right. It should pass. Yeah. Coercive, but I will come back to this. And then the YTD conjecture, the general one, the one which is not proven, says that this should be equivalent to K, or maybe uniform, but polystability. This should be equivalent to K semistability, and this to K instability, K unstable case. And one of the links, I will not expand on this, but one of the links is that this Donaldson-Futaki invariant that we saw in the first lecture should encode the slope of the functional M along some special geodesic rays in this space.
Sorry, what is your equivalence on the space of scalar potential? What is the equivalence relation there?
There's no equivalence relations. Oh, you mean to pass from potential symmetric?
No, I mean, you are saying that the function is well-defined, that is like a big theorem. So what is your equivalence there?
Oh, there's no, that's just that here I'm just defining M at by its derivative, sort of. And it says that I can integrate this, so it means that if I integrate this over a path, it does not depend on the path. Okay, and then, okay, so before defining coercive, the big statement, so convex along geodesic is due to Berman and Bernson. And then, so I will define coercive, but if M is coercive, this is equivalent to there exists a unique CSCK metric in omega 0. And this is due to Shen and Cheng for one direction. This is quite recent, from end of 2017. And for the other direction, is Darvas, Rubinstein, but also Berman, Darvas, Luch. So this is a big result. It's a resolution of chance conjecture. So, yeah.
So when you say M is coercive, you mean M is coercive along every geodesic?
I'll define coercive right now. Yeah. So coercive means it looks like this, means it grows at infinity, but you need to give a measure of what it means to grow at infinity. So I will give a definition. It will maybe not be so clear, but historically, it's the right notion. It would come with the statement that it is the right notion. Okay. So that will be, I'll start my next section on the analytic delta invariant, and I will start by introducing all the functionals, one of which measures coercivity. So this is due to Kewei Zhang. So I need to define some few other functionals. First is the entropy. So this is at first easy to, this corresponds to entropy notion for probability measures, so it's quite easy to write out. Unlike the Mabuchi functional, for which I did not give a closed formula. So I'm not normalizing stuff so that these are proba measures, but here I have a volume form. If I normalize it, it's a probability measure. Same for omega 0 to the n. This is entropy in classical terms. So this is one ingredient for defining the delta invariant. And the other, they actually form a big family. And I will use a kind of weird notation, which will be clearer tomorrow, to allow for even more functionals in this family. So I'll denote this by J exponent theta and index 1, comma C. I'll define it as the same way as here, so such that J1C theta of 0 is equal to 0, and this, we know it's infinitesimal variations. They look kind of the same. Take phi dot. I have the trace, so I should have defined this earlier. I will now. Of theta with respect to omega phi. So minus c times omega phi to the n. So it looks the same, roughly. Theta, okay. Theta is any closed real 1-1 form. So for any such form, I can define this, and C is a real number. I can define this functional. So this is maybe the definition is the fact that it is well defined is due to Chen, probably. And the trace of theta with respect to omega phi is this. It already appeared. Like the trace of Ricci of omega with respect to omega This is n times Ricci of omega, which omega n minus 1 mod omega n. This is the scalar curvature. I'm reusing this template, but putting other ingredients inside the trace. Okay. So from this we get the Shen-Tian. We can, okay, which order should I use? Maybe first the measure of coercivity. So this is by looking at the functional J1n omega 0. And this is something that goes to infinity when phi goes to infinity in K, whatever that means. So I can use this to define the coercivity of functionals. And then to define the delta invariant. So maybe let me put this here. M is coercive. There exists some eta positive. There exists a constant C such that for all phi in K, the Mabuchi functional is greater than eta times this functional minus C. So you should think of this as a norm. And this is the standard definition of coercivity on a finite dimensional vector space. So now I can define the analytic delta invariant. So for now, I worked with an arbitrary Kähler class. I can still do this now. To get the relation with the algebraic one, it will make more sense working with the anti-canonical Kähler class, but let's work this way for now. So this is the best coercivity constant for the entropy functional, not the Mabuchi functional. This is the definition. And now I want to prove that this controls the existence of Kähler-Einstein metrics on a Fano manifold. So using, of course, lots of results. But I'll do this. So maybe let me state before that this coincides with Hamid delta invariant. So this is a theorem by Kewei Zhang again. This definition is as well. Okay, let me write it in the first run class case, even though the statement is most likely more general. So we have equality of these two. This is, of course, a highly non-trivial theorem because with the next result, it sort of gives a proof of the YTD conjecture. I took anti-canonical. Yeah, Fano, because I took this as a Kähler class. So then X is Fano. No, I mean, the Kähler class is this one. But yeah.
You did on course.
And okay, probably the statement is more general, but I want to. Yeah. Okay. And then without assuming this, what I want to do in the remaining time is prove that this one characterizes the existence of Kähler-Einstein metrics. So again, this is due to Zhang, and but it relies on lots of results from the literature, even very strong results. If X is Fano, so same case is here. There exists a unique Ke metric on X. Okay, unique meaning the constant lambda is assumed to be equal to 1 as well. Otherwise, you can scale the metric. Okay. Let me write it this way. This is equivalent to this analytic delta invariant being strictly bigger than 1. Okay. So I'll explain this with the variational approach I introduced. Any questions before I start the proof?
Sorry, is that delta item driven on this road?
Yes.
Isn't this probably due to Thiago then?
More or less, yes. Yeah, that's just an explanation. I mean, it's not due to Chen because Chen never talked about the best coercivity constant for the entropy functional. But then we will use, of course, the Chen result. I mean, I'm not saying I will do a deep proof. I'm saying I will relate this definition with existence of Kähler-Einstein metrics using deep results. And the first one precisely is Chan's result. Yeah.
You never define what J is.
I defined it, but this way.
Oh, this is. I see.
You can write it down a closed formula, but it's not really enlightening.
And when you apply it, so can you replace that little c by n?
Yes, exactly.
For n is the dimension.
Yes. I mean, sort of, but both are possible only if there is discrete automorphism group.
So m being coercive is a property of x.
Oh yeah.
Yeah, and then that drawing should be read as in for all phi. Yeah.
For all phi?
Yeah. Or am
I mean, the phi lives in this. Yeah.
Okay.
This. Yeah. And I will talk about this tomorrow.
So am I right that each phi can be interpreted as a test configuration?
Not really. I mean, you would like this for geodesic rays. So not one phi, but you take a pass in the space of Kähler potentials.
So if that's the case, I see.
Yeah. And then that's not quite true either because test configurations are less than this, but that's really...
Okay, but at least all test configurations can be thought of.
Yes. Okay. So first step is indeed, so I'm using the way I presented stuff, but I'll do the remark of Rui right now. So first, recall that M coercive is equivalent to there exists a CSCK. But actually, for C1 of x, this is due. This is rather M coercive equivalent to there exists a KE metric. And this is due to Tian for the this direction, and to Fong Song Sturm Weinkov for the other direction, and it is much older than the Chen-Cheng's results and Narvaez-Rubinstein. But this is true. So at least we have this. We can interpret this as the existence of Kähler-Ricci metric means M is coercive. So now what I want to relate is coercivity of M with coercivity of the entropy. And that will be through the Shen-Tian formula. So that's another fundamental ingredient in the variational approach to canonical calorimetrics. So a good idea to mention this in this lecture. So that's the first step. Now, Shen-Tian formula for the Mabuchi functional. It boils down, I mean, it's due to Chen-Tian, but with the, once you know that all the functionals I wrote are well defined, it boils down to this simple observation. If I look at this thing, which appeared in the definition of the Mabuchi functional, then I can write it in a different way as, I mean, not get the signs wrong. Okay, this is omega phi. First part, minus, so I just plug in this. So this, I recall there, this is the scalar curvature, this part here. So I plug this in and I remove it, okay. Plus S bar. And I get something that looks like here, the thing defining the J functional. I mean, this is exactly one thing like this. And this turns out that if you work a bit, you can see that it defines the variations of the entropy. So you get that the Mabuchi functional writes as the entropy minus J functional, J1 S bar, Ricci of omega 0. So that's not quite, I mean, the entropy appears, so that's good. But then this term here is not quite the coercivity functional. So I'll work just a little bit to get this. So if omega 0 is C1 of x, then S bar is equal to n. So this is good. It's only the form above which is not good. And I claim that this is bounded, uniformly bounded So let me end the proof with this. That's really, I mean, for Rui, that's really not the deep part of any proof, but it's the occasion to give some examples of reasonings from this setting. Okay, let's first assume the claim. Then we can, we have that Mabuchi functional is equal to the entropy functional minus the functional encoding coercivity minus a bounded term. And then that means that if the entropy is bigger than delta times this minus C, this is equivalent to M being greater than delta minus 1 times this functional minus another constant. So you have this correspondence between the coercivity properties. And this is coercivity if this is coercive if this is greater than 1 than 0. This is positive over there. And that means delta, the definition, the analytic delta is bigger than 1, strictly bigger than 1. So that finishes the proof. And then for 5 minutes, I can prove the claim to give you some analytic techniques, basic techniques. I'll help you if you want to read papers on this. Okay. So the claim is more or less elementary, but let me write it. Okay. So remember the fundamental observation, which says that this lives in C1 of X. Then these two live in the same class, so the difference is IDD bar of a function for some function. Okay, then I'll look at variations of the difference of these two functional. So infinitesimal variations. I can plug in the definitions. I get the integral over x of phi dot times something. So really plugging in the definition, I get this. There's a cancellation, of course, from the n. And then the trace is linear. So I get this. And then one first basic ingredient of analytic Kähler geometry is integration by parts. That's here. It's what allows you to do this. And then the second ingredient is that the trace is the derivative of the volume, and that essentially tells you of the determinant. And that essentially tells you that this is equal to the infinitesimal variation of the functional which associates to phi the integral maybe I got the signs wrong. Yeah, there's a minus, but it's really not important. Get this expression, and then that means that j 1n omega 0 minus j 1n Ricci of omega 0. And this is the same as the difference of the values of this at phi and at 0. And this is less than the C0 norm of H times the volume or the degree of C1 of X. This is bounded independently of phi, maybe 2. Okay. So I'm running out of time. One other maybe thing I could have mentioned in the definition of delta is that from the definition it's always positive because the entropy is always positive. And that's used by another fundamental ingredient of analytic geometry, which is Jensen's inequality. So you can do this as exercise. And then another one that will not come in the lectures, but could have been in tomorrow's lecture is the maximum principle. And when you have all these ingredients, you can read papers in analytic Kähler geometry. So, yeah.
This analytical partner, which part is dealing with the assumption of the partner?
In this? Well, here. Yeah. So that means in this, the key thing is you can always write the Shen-Chan formula like this, but then this functional will not be related to the functional encoding coercivity in general. But you can really use this interestingly, so that will be probably in tomorrow's talk, but not as directly as here. Yeah. Okay, so I'll stop here. Thank you.